Hello everyone. We want to review how to find the length of a curve. So if I take a finite piece of curve here and I want to find its length, the easiest way to consider it is to break it up into a bunch of short little line segments and then find the length of each of those. So let's call the first one, let's say delta S1 and then delta S2 all the way down the line. And in fact, in general, let's call the ith one delta Si. Now, if I take one of these and I blow it up huge, this is the thing that I want to find. I'm going to estimate it with the line segment itself. Now this will form a right triangle, so let's call the change in x and the change in y the pieces, and I would establish a very simple relationship here. And that is that delta Si can be estimated by dSi, which would simply be the sum of the squares under the root. Now, in that, if I want to factor out the delta x squared from that quantity, this would become 1 plus delta yi over delta xi, quantity squared under the root, times delta xi outside the root. So we see if I wanted to add these up, a reasonable estimation, would simply be the sum from I equal 1 to n of all the little line segments, which would be the same as saying the sum from I equal 1 to n of this quantity, 1 in here, 1 plus delta yi over delta xi squared delta xi. So at this point here, if I take the limit of the Riemann sum, I find that the arc length itself would be the integral from a to b of 1 plus dy dx quantity squared under the root dx. As the Riemann sum, as delta x approaches 0, this quantity here becomes dy dx. So this is the formula that we generated in Calculus 1. Now continuing, instead of factoring out the delta x, what if we factored out a delta t? You say, well, I don't have a delta t, so let's introduce one. I could make this then delta xi over delta ti quantity squared plus delta yi over delta ti quantity squared under the root, and then pulling out the square of delta ti. So if you do a quick check algebraically, these quantities would be the same. So now when I take my limit, I'd be doing it with respect to t. So we have a different version of this integral where I'm going to have, in this case, dx dt quantity squared plus dy dt quantity squared under the square root integrated with respect to t, because the Riemann sum as the delta t's approach 0 would produce this quantity. But instead of going the x limits, I'll now have t limits. Let's generically call them from beginning t to end t. So now let's do an example. Let's find the length of the curve defined parametrically as follows. X and y are equal to this. Now, I would not be able to write this in terms of x and y by solving for t, but I can still find the length of the curve this way. So we'll start by finding dx dt, first times derivative of the second, so it would be negative e to the t sine t, plus second times the derivative of the first. If I factor out the e to the t, then that will leave me with negative sine t plus cos t, dy dt, which would be e to the t cos t plus e to the t sine t, and again, if I factor out the e to the t, so now the arc length parameter, which is the sum of the squares of these derivatives, so when I square this, I'll get e to the 2t times sine squared t minus 2 sine t plus cos squared t. Now when I add the square of this, I'll have e to the 2t cos squared t plus 2 sine t cos t plus sine squared t. Now you notice something beautiful happens when we add these together. These two terms are going to cancel. I'm sorry, that should be 2 cos t sine t. These two terms are going to cancel. I have a sine squared plus sine squared plus cos squared, which will give me 2 e to the 2t. So finally, the integral, which will be from 0 to 2 pi, will be of the square root of this, so root 2 e to the t dt, which is root 2 e to the t from 0 to 2 pi, or root 2 e to the 2 pi minus 1.